Hello, my name is Nastianevsky. We're up to section 5.6, which is the end of chapter 5. So chapter 5, we learned all about monoidal categories. And so this is a mini course on advanced linear algebra. So we had a course already, a mini course on linear algebra, just basic linear algebra, and now a little advanced. Now, linear algebra is a beautiful field. It is a humongous field, okay? And it's used all over in math, science, computing for sure, machine learning, et cetera, et cetera. And so there's a lot of different parts that we can choose to what we want as advanced linear algebra. So this is a short course, and basically what we do is we take those parts of advanced linear algebra that we'll need for other sections later on. Okay, so we're cherry picking certain topics in advanced linear algebra that we will use in quantum mechanics. We're going to have a mini course on quantum mechanics. We're going to have a mini course on quantum computing, and vector spaces, complex vector spaces show up all over for the rest of the book. So we need some of this stuff. Okay, and again, we all look at it. Of course, linear algebra is a part of mathematics, but we're going to look at it from the categorical point of view. Okay, let's just review what we saw in the basic setup. So we have the category K-vect. Okay, and K-vect, the objects are K vector spaces. K is a field, K-vect is a K vector spaces. The morphisms are linear transformations. Okay, so we saw that already. Okay, now, rather than dealing with an arbitrary K-vect, we're going to deal with complex vector spaces. Okay, so K is any field, it can be anything, real numbers, rational numbers, even the numbers 0, 1, Boolean reals, those show up also. But we're going to focus and we're going to talk about complex number vector spaces. And the reason for that is because they have the most uses. Quantum mechanics is mostly phrased in the language of complex vector spaces. Okay, but we also deal with, more importantly, finite dimensional vector spaces. Okay, complex finite dimensional vector spaces. Okay, so these two categories are our major concern, and of course there's an inclusion functor from here to here. Okay, so what else? Okay, over the past, in chapter 5, over the past things, we saw that these two categories have two monoidal structures, not one. One is called plus for the direct sum. Okay, and the other is the Kronecker product, or the tensor product of two vector spaces. And if you take finite dimensionals and you do this, you still end up in a finite dimensional. And if you have finite dimensional vector spaces and you take the tensor product, you end up in finite dimensional vector spaces. So these are two things. Let's just remember what the units for this is. The unit for this is the trivial vector space. So we'll do that. And the unit for this is the complex vector spaces. Okay, so we'll do that. Now, what we have to do is we have to boost up, since we're dealing with complex numbers, we have to boost up our knowledge about complex numbers, complex matrices, et cetera, et cetera. So that's what we're going to do a little bit of. Again, fairly quickly, because I assume you know complex numbers, but there is an operation called complex conjugation, which goes from complex numbers to complex numbers, and basically it goes a plus bi goes to a minus bi. Okay, flip the switch. Okay, and that's called complex conjugation. Okay. Now, if a number is real, that means b is 0, then let's just write it out. A plus 0i goes to a minus 0i. Okay, well, that doesn't change anything because 0 times I is equal to 0. And so you get, the main point is, if a is real, then a bar is equal to a. Okay, just in terms of categories and functors, if you like, It's not really its functions, but that's okay. If you think of this operation like this, and you have the real numbers sitting in the complex numbers, then this commutes, okay? It doesn't change the number. Okay. Very nice. Okay, that's fine for, that operation is for a complex number, okay? You need this, okay? But we can boost it up to an operation from complex matrices to complex matrices. Okay, let's just remember what this category is. The objects are natural numbers, and the morphisms from one natural number to another natural number is a complex matrix. Is a matrix with complex entries. Okay, let's just be formal about this. Okay, and it goes as follows. Take a complex matrix, a bar, sorry, let's leave out the parentheses. Okay, a complex number, a bar is a matrix. I have to tell you what the ij position of the A bar is, and the answer is it's equal to the ij position of the matrix, the ij entry of the matrix bar. In other words, what that means is take every single every single entry in the matrix and just do the complex conjugation of it. Okay, so instead of doing it on one complex number, do it on every single entry of the matrix. Okay, and just the repetition that real matrices, so let's do this, real matrices, let's just remember what this is. The objects are natural numbers, and a morphism from M to N is an N by M matrix. Okay, and this includes into complex matrices. In complex matrices. And this is the matrix conjugation. Okay, and basically the idea is, so the real matrices sit inside the complex matrices, and if you're dealing with real matrices, then this operation really does nothing, and that's what this commutes. That's what it means for it to commute. Okay. Next, more operations on complex matrices. Okay. Take a complex matrix. You could take the transpose of it. Okay, and this goes from complex matrices to complex matrices opposite. Okay, so let's be careful. If A is an a Mary by Nancy matrix, then A transpose is a Nancy by Mary transpose. So basically this goes the opposite way. So if you take an arrow in here from M to N, it's going to go to an arrow in here from N to M. Okay, let's put it formally. A transpose, the ij position of that, the ij entry of the A transpose is equal to A of j, come on. You flip what the ith row, jth column becomes the jth row, ith column. Okay, so this is the transpose. Okay, and great. And now we bring together the two operations of complex conjugation and transpose. So this is the transpose operation. And we get a new operation called the adjoint or dagger. The adjoint or dagger operation, and it goes as follows. Take the matrix A and you dagger it. Now that looks like a T, but it's a cross, okay, or it's a dagger. A dagger is a knife, okay, and it's defined as follows. The ij position is equal to A j comma I. What that means is flip it using the conjugation, using the transpose, and then take the conjugation of that. Okay. Now these two operations don't interact with each other. The transpose, in other words, you could do one in front of the other. They commute. Okay. So another way to look at this is take the entry, do the conjugation, and then flip the entry. Okay. Now, just categorically, the way we say this is complex matrices, conjugation, complex matrices. Okay. And then you can take the transpose and you get the complex matrices opposite. And here you get the complex matrices opposite. This is also transpose. And this is also conjugation, complex conjugation. And the main point is, here you're doing the conjugation and then the transpose. Here you're doing the transpose and the conjugation. And that's the dagger. Okay? We'll see later why it's called adjoint, and we'll see that you shouldn't be nervous about adjoint functors. So, similar to that. Okay? Now, main point is, not main point, but a side point, just relating real matrices and complex matrices. So, you have a nice operation of real matrices. You have a nice real matrices going to real matrices called the transpose. This sits inside complex matrices, which sits inside complex matrices, and this is dagger. Okay, so transpose is a special type of dagger where the complex entries, the BIs, the B's are all 0 for BI. Okay, so special type of complex numbers. Okay, one more operation, and that's called the trace. Okay, and trace goes from n by n complex matrices to complex numbers. Okay, and basically it goes as follows. Trace of A, where A is a square matrix, is equal to the sum of I equal 1 to n of A, I, comma, I. Okay, and the idea is, if you have a square matrix, add up all the elements along the diagonal, and that's called the trace of a matrix. Okay. We're going to use that too, but not so much. Okay, great. On top of page 269, I look at how conjugation dagger, it's a nice little chart, and trace, how they get along with a lot of previous operations that we had on matrices. So we learned a lot of earlier operations. So we have matrix addition, we have scalar multiplication. So take a matrix, take a complex number, you can multiply every entry in the matrix. That's called scalar multiplication. Okay. Matrix multiplication, take two matrices of the appropriate size and you can bring them together. You have the trace of a matrix. That's an operation we just saw. I'm sorry. I did trace over there, sorry. Direct sum and tensor product. So we have these 5 operations, and we brought in these 3 new operations, and we want to make sure how they get along. So let me just show you some of them. So matrix multiplication, A dot B bar is equal to A bar dot B bar. Okay, and the same thing for dagger. A dot B dagger is equal to A dagger dot B dagger. I just want to show you how trace gets along with matrix multiplication. This is interesting. Trace of A times B is equal to trace of B times A. That's A times B is not equal to B times A, but the traces are equal to. Okay, let's do another one. A tensor B conjugation is equal to A conjugation tensor B conjugation. Okay, anyways, we have 5 previous operations, we have 3 new operations, so we have 15 different equations to do it. We'll do one more. Scalar multiplication and dagger is as follows. C dot A, so A is a complex matrix, C is a scalar complex number, dagger equals C bar, that's complex conjugation of a complex number, dot scalar multiplication of A. I'm sorry, I think that's an A dagger. A dagger. So it doesn't really preserve, but it preserves it up to C bar is conjugated. Okay? Okay. Anyways, you have to do this. I mean, you have to stare. Basically, most of them get along the way you would think they get along with. I guess this is out of context. This is wrong. This is wrong. I think it's B dagger dot A dagger. Okay, that transpose swaps things. Yeah, so, sorry, that was wrong. But now we fixed it. Okay, great, let's go further. Okay, so lots of new operations, and you have to see how the operations, dare I say it, cohere with the old operations. Okay, great. Now, next. So now we have a lot of extra structure. We know a lot of extra things about complex numbers. Very nice. Okay, but now we're going to build further. So what we're going to do is we're going to take vector spaces and we're going to add extra structure to them. Okay, and we're going to describe them. Okay, so the extra structure, so we're going to have a typical vector space V. We're going to add an extra structure called like this. And this is called the inner product. Okay, so what is it? It's a function, sorry, it has a comma there. It's a function that from the vector space across the vector space to the complex numbers. It's a function that compares 2 vectors. So this is something we never had before. We had a vector, we can add vectors, we can scalar multiply vectors, but now we have something new. We want to be able to compare 2 vectors. So we take 2 vectors and we get out some number that describes their relationship, in a sense. Okay, now this operation has to satisfy certain requirements. For example, little v plus little v prime, comma, little w, so you have 3 vectors there. We want this scalar, this inner product, to preserve this operation, okay, in some sense. So what that means is this. Okay, this plus is inside the V, capital V. This plus is inside complex numbers. Okay. Okay. Same thing with the other side. So let's just write it out. Little v, sorry, little v little v, comma, w plus w prime is equal to v, comma, w plus, again, that's in complex numbers, v, comma, w prime. Okay, so that's how the inner product gets along with the addition of the vector space. Guess what we're going to ask now? How does the inner product get along with the scalar multiplication? And the answer is as follows. It's a little bit more complicated. C dot little v, comma, w is equal to exactly what you think it is, C times v, comma, little w, okay? Now, let's go through this. This dot is the scalar multiplication of v. This dot, that's a complex number, that's a complex number, so that dot is complex multiplication. Okay, which is a scalar multiplication of the vector space complex numbers. So that's one thing. Okay, but it's a little bit more interesting, and we say this is linear. Okay, it's a linear. Well, basically what it's saying is, here's a vector space, here's a vector space, this is a vector space, this is a complex vector space, this is a complex vector space. This should be linear. It should respect, we saw it as respects the addition, great. Now we want it to respect the scalar multiplication, very nice. Okay, but it gets more interesting. Okay, and the answer is, it's like this. How about v, comma, c dot w? Okay, and again, that scalar multiplication is in v. Okay, well, it should equal to c bar, complex conjugation of v, comma, w. Okay, and this is called antilinear. Very nice. Okay. So this takes care of this. This coheres with, this is the way inner product coheres with addition. This is the way inner product coheres with scalar multiplication. One more property, okay, and this is called skew symmetric. S-K-E-W, symmetric. Okay, and that says, hey, what happens if I flip UV? What's the relationship? Okay, so if you're dealing with real vector spaces, then you have something like this. V, comma, W is equal to W, comma, V. Okay, and what that says is, when you're comparing two vectors, it doesn't matter which one's first and which one's second. And that's very nice for real vector spaces. Okay, but life gets much more interesting with complex vector spaces, and so we get the following. V, comma, W is equal to W, comma, V conjugation. That's complex conjugation. Okay, so when you have that, that's, okay, so that's what the inner product has to satisfy. And again, it's a little bit more complex. It's this here, it's the same as real vector spaces. This and this is a little bit more complicated with complex vector spaces. Okay, great. So this is a nice example. This is a nice definition of what an inner product has to satisfy. Now we'd like to see an example. Okay, and in the book I give a few examples, but I just want to highlight one example because it's the most important example that we're going to do, and that's C to the n. So that's a complex vector space of vectors, okay, with complex entries, n vectors with complex entries. Okay, great, that's a typical vector space, and I'd like to know what the inner product is for this. And the answer is, if you have a vector v, that's n complex numbers, and you have a vector w, that's n complex numbers, then their inner product is v dagger times W. Okay? Okay, let's just go through this. The vectors you should think of as long n by 1 matrices. So the dagger of that is a long column, okay? And this W is going to be a long, that's a column, that's a row, okay? And the scalar multiplication is going to bring this across this, and you're going to get out this number times this number, this number times this number, dot, 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 this number times this number, add them all up, and you get some number of the complex numbers. Okay, so that's our primary example that will be important later on. Okay, now let's do this. If V and W are vectors and we're comparing them, we get this. If they're equal to 0, we say they're orthogonal. These vectors are orthogonal. Okay, great. So let's go through this. We have complex numbers and we have inner products. We use this inner products to make other definitions, to describe other structures. So let's talk about that. Okay. The one thing is we could take the norm. We've seen this before, but the norm of a vector. Okay. And so we write it like this. Here's V. So let's just fix our idea. We're in a vector space and we have an inner product. So we call this an inner product space. So we can just find the norm of the vector, and that's basically, it's V comma V. Okay. Now, if you think about what this is in terms of complex numbers, C to the n, so this, they're all real numbers. I'm sorry, you add them all together. So V conjugation comma V, when you multiply them out, you get a real number. And so when you add up all the real numbers, you get a real number, and then you could take the square root of it. So that's basically to be thought of. It's not real, but to be thought of as the length of the vector. Okay. Given such a thing, you can also talk about the distance between two vectors. So there's a functor d comma this. It takes two vectors, okay, and it outputs a real number. Sorry, I should have done the same thing. Norm takes a vector and outputs a real number. Okay, let me show you how distance is defined. D of V comma W is equal to the norm of V minus W. Okay. Okay, let's just write this up. This is the square root of V minus W comma V minus W. It's the norm of V minus W. Okay, now norm and distance satisfy different requirements. They satisfy some type of triangle inequality. They satisfy some type of non-degeneracy. You'll see it in the book. You can read it. You can watch it. You have to read it. Okay. One more definition of that uses this inner product. Okay, and the idea is as follows. Let's say you have a linear transformation, which goes from V comma W, V comma inner product of V. That's one thing. Okay, and you get out W comma inner product of W. That's a capital W. That's a capital V. Okay, Okay, great. So what is it? Well, it's a function from v to w, which is linear, so it's a linear transformation. So it respects the addition, it respects the scalar multiplication, but also we have to talk about this. Okay, there will be certain certain linear transformation, which we called bounded. Okay, and the idea is this should take a vector. A vector here should go to a vector here, but it shouldn't change that much. Okay, and I'm not being exact by what it means. I mean, in that English, I'm not being exact, but let's be formal about it. What do we mean by this? It means as follows. For all little v in there, okay, we want that t of v, okay, and we can look at the length of that one. So we shouldn't shrink or extend that much. Now that's a vector in W. So this is a norm norms are described by the vectors. So this is a norm in W. It should be less than or equal to, okay, Okay, so let's do this again. We'll do this again. T is, from here to here, is bounded if there exists an R of T. Let's write this over here. R of T, it's capital T, so it's a real number. Okay. More than 0, so it's a positive real number, member of the real numbers. Okay, so it depends on t, but it doesn't depend on v, little v. Okay, so it's r of t of v, that's little v, and that's capital V. Okay, so let's go through what this is. V is a small vector in V. It has a certain length. Okay, it has a certain norm. Okay, T of V also has a certain norm. Okay, the norm of V is here, the norm of T of V is here. Well, we want them to respect each other. We don't want them to grow too far, be too big, or be too small. So we have that. Okay, if this is true, then what we say is that the linear transformation is bounded. Okay. Okay. Next, we're going to talk about bases. So let's see how these inner products help us with bases. Okay. Okay. So given a basis, there are different things we could do with the basis. First of all, we can describe different types of bases. So one of the things we want to talk about is an orthogonal basis. Okay, what's an orthogonal basis? That's a basis that if you choose any two different elements, if I choose different elements, that implies that when you compare them, their inner product is equal to 0. So any two different basis elements are orthogonal to each other. Okay, so that's an orthogonal basis. Then we have something called a normal basis. What does that say? That says take any element, bi, and another bi, okay, their norm is 1. I'm sorry, their inner product is 1, so their norm is 1. Okay, which means they kind of are little equal arrows, the same length. Okay, 1. Okay, and then there's an orthonormal basis. So that's combining these two, orthonormal. And basically it says, if I is equal to j, then it's equal to 1. And if I is not equal to j, then they're equal to 0. So the way you write that is bi comma bj is equal to, again, it's both orthogonal and normal, okay, delta I comma j, okay, where this is the Dirac, the Kronecker delta. Okay, this is equal to 1 or 0, depending on if they're equal or not. Okay, great. So again, this is, you have a basis. These are nice bases. This is also a nice basis. This has all the nice properties you want. Okay, so what do we want? What are we going to get out of this? Okay, so so let's say we have a really nice orthonormal basis. Okay, and let's say we have a vector v in this, or we have this vector in this vector space. So we have a giant vector space and we have a basis on it. Okay, so one of the things we could do is, write v in terms of this basis. So that's C1, B1. Okay, C1 is a complex number, B1 is one of these bases, plus C2, B2, plus plus Cn, Bn. Okay, so that's the vector written in this basis form. Okay, good. Now let's do the following. Let's write v. Okay, and let's measure v in terms of bi. Let's measure it in terms of compare it to one of the bases. Okay, so this is equal to C1, B1 plus C2, B2 plus plus Cn, Bn, comma, the bi. Okay, now we have linearity. We have linearity in terms of this. There's lots of pluses there, and there's lots of multiplying like this. So basically, this is going to turn out to be, and again, I do all the steps in the book, C1 times B1, comma, bi, okay, plus C2, comma, B2, comma, bi, plus plus CNBN comma bi. Very nice. Okay, so when you measure a vector with this bi, you're going to get this thing. Now, by orthonormal, the fact that it's orthonormal means that if B1 is not equal to bi, this goes to 0. If B2 is not equal to bi, this goes to 0. If Bn is not equal to bi, this is 0. If it is, it's going to be equal to, okay, if they are equal, okay, if let's say I is equal to 1, then this goes to 1, this becomes C1, all the rest becomes 0. So all of these terms, for all of these terms, they're all going to either go to 0, for the most of them, they're going to go to 0, except for one, where this is bi. So this whole thing is going to equal to Ci. Okay? In other words, the coefficient of bi. Right? In the vector v. Okay, great. So now, here's another way of writing v. V is equal to, okay, let's use this fact. V is equal to V comma B1 plus V comma B2 plus plus V comma Bn Bn. Okay, in other words, the coefficient times the one basis element, the coefficient times another basis element, etc., etc. Okay, now this is going to be very important later on in quantum mechanics. It's going to basically say, well, it's important in linear algebra. It basically says that we can use the inner product to determine the coefficients. In other words, what this is saying is how much this vector v, how much is it in the b1 direction? How much is it in the b2 direction? How much is it in the bn direction? Okay, so that's very important. And it all follows from using an orthonormal basis. Okay, great. Okay, so we have a complex vector space. We have this extra structure, namely an inner product. Okay, we need a little bit more to get what's called a Hilbert space, and a lot is built on Hilbert space. Okay, now I'm going to go through this, but I guess I have to say we don't really have to worry about it because it's not going to be used that much, but we do have to go through it. So we're going to call a sequence of vectors. So you have a vector space and an inner product. The inner product also gives you a norm and a distance function. Okay. Okay, so great. Now let's see if we can use this. So we say as follows: v1, v2, v3, dot, dot, dot. Here you have a sequence of vectors. The vectors are in the vector space. Okay? Such a sequence is called a Cauchy sequence. Let's see how to spell it. Cauchy sequence. If it satisfies the following requirement. Okay, and the idea, let me just give you the idea. The idea is that these vectors get closer and closer. Okay, and the way to say that they get closer and closer, it says as follows, is for every epsilon greater than 0. In other words, when I say something gets closer and closer, I mean, how far are they? Okay, so epsilon, when they're epsilon separated, when they're epsilon away, okay, comma, there exists a n0. Well, there is some big n0 that's a member of the natural numbers. Notice these are indexed by the natural numbers. Leave out n0, okay? Leave out 0, such that, let's write it out, such that for all m comma n greater than n0, whoops, I want to make that bold-faced. I want to n0. The distance of Vm, comma, Vn is less than epsilon. Whoops. Epsilon. Less than or equal to. Okay, let's just see what it says. What it says is, what it really says is, as you get further and further, these get closer and closer. Okay, but let's try to follow the thing. It says, as close as you want it. How close do you want it? You give me any e telling you how close you want it, then I'll give you some n0, and I'll say, and we'll say for that for all the numbers after that n0, so here's your sequence of vectors, there's some n0, and for everything further than that, for all m comma n in here, so here's a little m, here's a little n, or it could be the other way around, okay, d of vm, so here's vm, and here's little vn, is less than, the distance between them is very small. Okay, so that's called a Cauchy sequence. Again, what this is used for, we don't need to know. Okay, this is not going to be used in the rest of the book, but that's a formal, nice definition, a little bit calculus-based, okay? For those of you who have taken calculus, this is the delta epsilon definitions, things like that, but we don't want to talk about that. What we want to say is as follows: an inner product space, that's what this is, a vector space and an inner product, okay, is complete if for every, say it exactly, okay, so we're defining the word complete. That's a definition, okay? If for every Cauchy sequence, I'm sorry, V1, V2, V3, maybe we should start at V0. V3, okay? For every Cauchy sequence, the limit as n goes to infinity of the distance of for every Cauchy sequence, there is a vector v, we'll say v hat, okay, such that the limit as n goes to infinity of v to v hat, okay, is equal to 0. V hat is in V. Okay, so let's say it again. An inner product space is complete. That means you get what you're aiming at. It's complete if for every Cauchy sequence, like that, okay, there is a vector v hat such that the limit as n goes to infinity, in other words, as n gets further and further, the distance from Vn to V is equal to 0. Okay? In other words, here's your vector space. If you have some sequence like that and it's going and going, okay, then it's eventually going to hit something in there. Okay? If you have a bunch of vectors that are closer and closer and closer, eventually it'll hit that one. Okay, great. Now, another definition. A Hilbert space, okay, and that's what we're aiming at the entire time, okay? So these are the types of complex vector spaces that we're going to be dealing with for a lot of the time, okay? A Hilbert space is a complex inner product space that is complete. Okay, now what this completeness has to do and why it's so important is a little bit beyond us, okay? In quantum mechanics textbooks, they talk about that, and in a lot of uses they talk about it, but we don't have to worry about that. Let me tell you why. Because for the most part, we're going to deal with finite dimensional Hilbert spaces. And all finite dimensional Hilbert spaces are automatically complete. So what that means is that if we have an inner product space, a complex inner product space, finite dimensional, then it's already a Hilbert space. We don't have to worry about it. Okay, great. So this was what we were aiming at. And now let's talk category theory. Okay. when we talk category theory. So there's the category of Hilb, which is Hilbert space. Let's say what it is. You ready? The objects are Hilbert spaces. Very nice. And the morphisms are bounded linear operators. So let's just remember what we just did, bounded linear operators 10 minutes ago. What that is linear operators that don't stretch things or extend, shrink things too much. Okay, so that's the category of Hilbert spaces. And we're going to have a subcategory, finite dimensional Hilbert spaces. Okay, and what's that? Those are finite dimensional Hilbert spaces with bounded linear operators. Okay, now, okay. Out of this inclusion, we also have complex vector spaces. Okay, and we have finite dimensional complex vector space. Whoops. I think we read it the other way. So we have complex finite dimensional vector spaces. Okay, and that includes into this. Okay, great. Next, there are forgetful functors, like that. In other words, given a Hilbert space, you can forget about the inner product and the fact that it's complete and go to complex vector spaces. Okay, same thing with finite dimensional vector spaces. Okay, great, but we're not done. Okay, because Hilberts and finite dimensional, they're not only vectors, they're not only categories, they're monoidal categories. We're in chapter 5. We're talking about monoidal categories. So what we want to do is talk about the monoidal structure here. But there are two monoidal structures here. So let's talk about them. You ready? Given V and W, these are two Hilbert spaces, we can talk about V plus W. Okay, well, we need to find an inner product space for this. Okay, so yes, so this has, we showed this is a complex vector space before, but now we have to show that it has an inner product space. So we have to talk about this, an inner product of V plus W. Okay, so what are the typical elements of V plus W? Well, there's a little v, comma, a little w, and another typical element is another v prime and another w prime. Okay, very nice. Okay, so what should this equal to? And the answer is, this is equal to v, comma, v prime, which is an inner product in capital V, plus W, comma, W prime, which is an inner product in W. And we make that plus. This is plus of complex numbers. So that works. Okay, that's great. That discusses the inner product of, that discusses the direct product of Hilbert spaces. What about the tensor product of Hilbert spaces? So given a vector space, tensor product of V tensor W. Okay, and the answer is, okay, so we can make an inner product here also. Okay, so we're going to call this the inner product of V tensor W. Okay, and a typical element here will be V tensor W. Okay, we want to compare it to another typical element here, which would be V prime tensor W prime. Okay, and the way this is defined, and it satisfies all the requirements, is this is V tensor, V comma V prime tensor, multiplication. So this is in V, that's a complex number, times, that's complex multiplication, W comma W prime in W. Okay, great. We have to show, obviously, this satisfies all the requirements. We have to show this satisfies all the requirements of being an inner product, et cetera, et cetera. But what we get out of this is, I don't want to talk about this right now. What we get out of this is that not only is Hilbert space a category, but that's a monoidal category. Okay. By the way, it is not a strict monoidal category. It's okay. Similar here. Okay, that's a monoidal category. Okay, that's one monoidal category, and here's another one. Plus and 0. Plus and 0. So we have two monoidal category structures here, two monoidal category structures here. We're going to see later on how they interact, how these interact. Anyways, they interact the way they're supposed to interact very nicely. We'll see that later on in chapter 6 when we start talking about how relationships between monoidal categories. But right now we don't have that. We just know that this is a monoidal category, this is a monoidal category. Anyways, but that includes. Okay. So we have the category of Hilbert spaces, and we have the monoidal category. I'm sorry, I shouldn't say the category. The monoidal category of Hilbert spaces, two monoidal categories of Hilbert spaces. Very nice. Okay. Now we need something about operators. So what's an operator? That's a morphism from V to V. Let's just talk about morphism from V to V. Okay, so what I want to do is I want to focus for a second on matrices. Okay, so we're going to start with easy matrices and build up to harder matrices, and then we'll connect that to vector spaces and stuff like that. So, you ready? So let's talk about real matrices, because this you might have seen before. So we have two types of real matrices that are important: symmetric. Okay, and an A is an n by n matrix. Okay, it's symmetric if A transpose, if you flip those things on the rows and the columns, it's equal to A. Such a matrix is called a symmetric matrix. Okay, and besides that, you have something called an orthogonal matrix. Okay, and that says A transpose is not equal to A, but it's equal to A inverse. Okay, but more important, what that says is A times A transpose is equal to the identity, which is equal to A transpose times A. So if this is the inverse, A times the inverse is the identity. So these two requirements are the same. This is for real matrices. Now we need the complex version of these two properties, complex, okay, and they have slightly different names. They have different names, okay. We call a matrix Hermitian. A complex matrix, we call a complex matrix Hermitian if A, we're not going to use the transpose, we're going to use the dagger, okay, is equal to A, okay, and we're going to say a matrix is, we're going to use the complex version of this, is unitary if A dagger is equal to A inverse, just like before. Okay, and again, we have that same trick. Another way of saying this is that A times A dagger equals identity, which equals A dagger times A. Okay, these two will be fundamental. These two are the two building blocks of all of quantum mechanics. Okay, let me just foreshadow for a second. The unitary matrices, complex systems change with as unitary matrices. When you measure a quantum system, you use Hermitian matrix. Okay, great. Now, so these are special types of matrices. Okay, and we have to look at their properties. with respect to other operations. So I'm just going to read to you 5.6.7. It goes as follows. This is a theorem. The set of Hermitian matrices, now we're talking about this. We just use this to come up to this, but now we're going to talk about these two. The set of Hermitian matrices is closed under matrix addition, direct sum, Kronecker product. In general, the set of Hermitian matrices is not closed under scalar multiplication and is not closed under matrix multiplication. Okay, what I'd like to just show is why it's not closed under matrix multiplication, because that's going to have a lot to do with us. Okay, so take two matrices, A times B. Take the scalar product and take the tensor product of that. We would love if that's equal to the original thing. That's what it means for it to be Hermitian. So question, is A times B Hermitian? Well, let's see what this is equal to. This is equal to this is equal to B dagger times A dagger. Okay, now assume that A and B are Hermitian. Okay, we're going to assume A and B is Hermitian. We want to know if A times B is Hermitian. So if B is Hermitian, so then B dagger is equal to B. So this is B. If A is Hermitian, then A dagger is equal to A. Okay, great. Okay. Now, question, if A times B is Hermitian, okay, then A times B dagger is going to equal to A times B, not B times A. This is not equal to A times B in general. Okay, for 1-by-1 matrices it is. Okay, conclusion, Hermitian matrices are not closed under matrix multiplication. Okay, and so that theorem listed off where it's what it's closed under and what it's not closed under. This is something typical. Whenever we introduce a new operation, okay, these are new operations. We have to see how it gets along with the old operations that we dealt with. That's coherence theory. That's category theory. Okay, next. So we talked all about Hermitian matrices. Let's talk about unitary matrices. Okay, theorem 5.6.8. The set of unitary matrices is closed under matrix multiplication. That's important. Direct sum, Kronecker product. In general, the set of unitary matrices is not closed under matrix addition and scalar multiplication. Okay, so they kind of have opposite properties. What I'd like to focus on is matrix multiplication. So let's talk about that. Okay, so ready? So let's assume A is unitary. Let's assume B is unitary. And I want to know if A times B is unitary. Okay, so how do you tell if A times B is unitary? I'm going to follow this. Okay, well, multiply it by A times B dagger. Okay, and see if you get out the identity. So again, A is unitary, B is unitary. I want to know if A times B is unitary, so we get this out. We're going to try it like this. See if this is satisfied. Okay, so let's see what we get. Then we get A times B. Matrix multiplication is associative, so let's leave out brackets. Let's leave out parentheses. A times B dagger is equal to B dagger times A dagger. Okay, now we assumed that B is unitary. What does that mean? That B times B inverse is equal to the identity. So this whole thing becomes the identity. So we get this. Okay, which the multiplying by the identity doesn't change anything, so we get this. A times A dagger. But 1 second. A dagger, A times A, we assumed A is unitary. So this is equal to the identity. Conclusion, A times B is unitary. Okay, that's very nice. Okay, Great. So, conclusion. Hermitian matrices are not closed under matrix multiplication. Unitary matrices are closed under matrix. Okay, let's see if we can use that. Okay. Okay, it goes as follows. Let's put all our information together. You have real matrices, you have complex matrices, okay? I'll explain that in a second. Okay, this is a new category. It's called U matrices. It stands for unitary matrices. Okay, and the idea is as follows. The objects are the natural numbers, just like here the objects are the natural numbers. But here, the only matrices, the only arrows are unitary matrices. And the main point we just saw was unitary matrices is closed under matrix multiplication. Matrix multiplication is composition in this category and in this category. So it forms a category. Unitary matrices form a category. Okay, now real matrices, all four of these categories, the objects are the natural numbers, the morphisms are matrices. Okay, here they're orthogonal. I should put this. Here there are orthogonal matrices, and again, just like unitary matrices are closed under matrix multiplication, orthogonal matrices are also. Okay, so this is the big thing we're dealing with: complex matrices. Some of them are unitary, some of them are real. Okay, and we get like that. Okay, great. But there's another side to what we're talking about. Okay, and the other side is as follows. Hermitian matrices. Now, Hermitian matrices do not form a category. And the reason why they do not form a category is because it's not closed under matrix multiplication. Composition is matrix multiplication. So they don't form a category. So we're going to talk about the set of Hermitian matrices. Okay? For the same reason, symmetric matrices are not closed under matrix multiplication. Okay, so we have not the category symmetric, not the category of symmetric matrices, but the set of symmetric matrices. Okay, and if you want, you can think of this as a big graph. The objects are natural numbers, and the morphisms are symmetric matrices. There's no composition. Okay, this includes into this because symmetric matrices, they satisfy ST for the transpose. These satisfy the dagger. Okay, and that puts everything together. These are all subcategories of complex matrices. It's very pretty. Let's leave that alone. Okay, great. New topic. T goes from V to W. So that's a bounded operator. Okay, and we could talk about the adjoint. Oh, we see that word again. Or dagger of the operator. So we're going to talk about T dagger. Okay, the dagger goes the other direction, W to V. Okay, so let's just go through this. Given this, there might exist this. We'll talk about when it exists or it doesn't exist, if the following is satisfied. for all V in W, for all V in V, for all W in W, T of V, comma W. Okay, now where's this comparison taking place? We have T of V, that's an element of W. We have little w, that's an element of W, so this is in here, is equal to V, comma, T dagger. T dagger goes from W to V of W. And this comparison takes place here. Okay, so if this is satisfied, this is called, if this is satisfied, then T dagger is called the adjoint or the dagger of T. Okay, now, any category theorist in all would say, hey, that's an interesting name, adjoint. That's like left of V, comma W, let's put a ham over here, okay, is equal to, isomorphic to, ham of V, comma, right of W. Hey, this is back to chapter 4. Okay, but the main, and that's true, that's the analogy here. The only thing is, adjoint linear vector spaces, okay, is way older than category theory. Okay, so this is from the 1800s, they were dealing with this stuff. So this is way older than category theory. In fact, category theory stole the language from linear algebra. So yes, you should notice this, but just realize what came first. Linear algebra had this first. Okay, good. Okay, great. Okay, now comes a theorem or definition. Definition: T is self-adjoint if T bar equals T. What that means is, you ready? Erase this. If T satisfies this, I'm sorry, this is going from V to V. Okay, so we're going from one to the other, from one, between two vector spaces, we're going like that. So it's called self-adjoint. Okay, now we've seen something like this, T star to T, and this has to do with, that's Hermitian matrices. So, you ready? Let's remember. So this is self-adjoint or Hermitian. So let's just remember the following fact. A matrix, an n by n matrix, okay, then we have T of A. Okay, what's T of A? This goes from Cn to Cn, and the idea is as follows. T of A of some vector is equal to A times the vector. Okay, so let's go through this. This is a vector, so this is an n by 1. This is an n by n. When you multiply it, you get an n by 1. The output's like that. So we saw this before. Okay. And what this does is it relates the world of matrices to the world of operators on vector spaces. Key point. This is very important. So this is about complex matrices. Okay. A is a complex matrix and complex vector space. Okay. And now we're going to see the relationship between that in a second. Okay, but so we took we were talking about complex vector spaces. We took a break from that for a second, and we talked about complex matrices, and now we're going to relate the two. Okay, Okay, great. Okay, we had the category of Hilbert spaces, and we had the category of finite dimensional Hilbert spaces. Okay, now I want to talk about two other categories, namely U and U. Okay, so let's say what these categories are. The objects here are Hilbert spaces, just like before, but the morphisms are just unitary matrices. Okay, now unitary matrices are very interesting because they have very nice inverses, right? The adjoint is their inverse. Okay, same thing here. So we're going to have this. Okay, and we have to talk about the two monoidal structures. So they form like this. Okay, but there's something important here that has to be mentioned, that has to be go through. It's a very subtle point. And the idea is as follows. Let's say you have a Hilbert space, and you have another Hilbert space. Okay, then this is the direct product of them. Okay, and so we can go like this is the direct product of them. Okay, now let's write that neatly. Now, it's not only the direct product, it's also the direct coproduct. Okay, so I can talk about inclusions of this into this, or I can talk about projections from this into this. Irrelevant. Okay? In the category of complex vector spaces, that works out. In the category of Hilbert spaces, that works out. But in the category of unitary Hilbert spaces, these morphisms are not unitary. In general, these are not unitary. Unitary means they have this, they're invertible, they're isomorphic. These two are not isomorphic. These two are not isomorphic. There's usually an inclusion, there's usually a projection. So it's a very subtle point. Given two Hilbert spaces in this category, there is another Hilbert space like this. However, and it's the product and it's the coproduct. However, the morphisms, it's the product and the coproduct in the category of Hilbert spaces. However, in this category, it's not the product and the coproduct because there are no projections and there are no non-trivial projections and there are no non-trivial inclusions. So a very subtle point. It exists, but it's no longer does it have the universal property. Okay. So again, the category of unitary unitary operators and Hilbert spaces has a monoidal structure, but this monoidal structure is not the product and the coproduct. Okay. Same thing for here. Okay, but what about tensor? Well, it has a product and coproduct, just like before. This is complex numbers. This is complex numbers. It has a coproduct. Well, anyways, in the category, it's not, no one ever claimed that this had universal properties, so we don't have to worry about this part. Okay, anyways, all these four, these two and the two I just erased, products exist. Okay, great. Want to make one big, beautiful picture, and it has everything that we've spoken about till now. It's on page 277. It goes as follows. You have set complex vector spaces. Hilbert gets into that, and U Hilbert includes into that. Okay, we're going to build this further on. Ready? Between any set and complex vector spaces, you have adjoint functors. And the adjoint functors basically give you the free, the set of basis elements. It gives you the free complex vector space over that, okay? And also you have a complex vector space. You can forget the operation, you get that. This is chapter 4. Now we go on like this, okay? And we talk about the category of Hilbert spaces. So what's this? This is a complex vector space with an inner product that's complete. Forget the inner product. It goes like that. Okay, great. Now let's go here. Here's bijective on objects. Both of these categories have Hilbert spaces and objects, but this only has unitary matrices. Unitary operators as morphisms. Very nice. Okay, we're only 1/3 finished. Okay, great. Included into here is finite sets. Now we're going back to chapter 1. Okay, and including into here is finite dimensional complex vector spaces. Okay, and there is a free functor here, which is an inclusion of this, so this commutes. Okay, but we pointed out before, take a finite dimensional complex vector space, forget the complex vector, you don't get a finite set. So there's no morphism going the other way. Okay, in some sense, this is the most abstract. Now we're getting down to the more concrete. Finite dimensional is more what we see in some sense. Okay, great. Now you have also finite dimensional Hilbert spaces. Okay, and you can forget that. Very nice. Okay, and you have also inclusion of that. So let's just remember what this is. The objects are finite dimensional Hilbert spaces. The morphisms are bounded linear operators. That's very nice. And you can also have, what do I call it? U finite dimensional Hilbert spaces. Okay, let's go through this. The objects are Hilbert spaces, finite dimensional Hilbert spaces. The morphisms are unitary maps, unitary operators. Okay, so infinite, lots of infinite up there in the sky, more finite dimensional, very nice, but we can go one step further, okay? Namely, complex matrices, okay? And we talked about there's a lot of different type of matrices within this category. There's a lot of interesting subcategories here. Okay, they're given any matrix. There is. I'm sorry. Let's go through that again. Sorry. Let's do, this is very important. So let's do this. The objects here are natural numbers. The objects here are finite dimensional vector spaces. In particular, the n over here, that's the natural number here, is going to go to, that's an arrow, c, that's a maps to c to the n. Okay, c to the n, which is a complex vector space. Okay, and a vector here from, a morphism here from n to m is an m by n matrix. So that's going to be like this. This is going to go to c to the m, and I might have the arrow the wrong way. No, not to worry about it. That's going to go to a matrix A. So this is going to be an matrix A. So this is going to be T of A. Okay, so that's that connection between matrices and finite dimensional vector spaces. And finally, U matrix. Okay, one of the subcategories of complex matrices, in fact, the only subcategory that's important. We're not interested in symmetry. We're not interested in orthogonality because that's reals, okay? And we're not interested in Hermitian matrices because that doesn't form a category and hence doesn't belong here. So the only thing we are interested in is unitary matrices. That includes into this. I'm sorry, I didn't finish this. So again, the same thing. The natural numbers go to c to the n, okay? Main point is, this is an equivalence of categories. And so too here, this is an equivalence of categories. N goes to C of N, and a unitary matrix is going to go to a unitary operator here. In some sense, this is the most concrete. So up in the air, finite dimensional, more down to the earth, this is the most concrete. This is the thing that we have operations on. This is the thing we will operate on. Okay, so this picture is a very pretty picture. It's on page 277. But we're not finished with this picture, okay, because this doesn't include all the operations that we have here. This is a diagram of categories, but we're in chapter 5 already, and we're big boys and girls now, and so we should talk also about the products and the coproducts and the monoidal structure here. So for example, set has 2 monoidal structures, namely plus disjoint union and Cartesian product. Complex vector spaces has 2 monoidal structures here. And we can talk about that. The inner product and the tensor product. Same thing here, same thing here, same thing here, same thing here. So we will, and so again, these are all categories. However, they all also live in the category of monoidal categories, and these functors all respect those operations in some sense. Okay, so this is just the beginning of what we'll see later on in chapter 6 when we talk about how I've drawn all of these different categories with their different structures, but I haven't talked about morphisms between monoidal categories. In chapter 6, we'll talk about morphisms between these monoidal categories, and we're going to see 2 versions of this. One with the direct product, or plus, okay, and one with the tensor product, or Cartesian product. And it all fits together absolutely beautifully. Okay, great. Let's finish off this section fairly quickly. Okay, and the idea is as follows. Eigenvalues and eigenvectors. And the idea is as follows. You have t from v to v. Okay, and if you have some vector v, such that this is equal to lambda of v, okay, what this means is it's not a fixed point, but it's fixed point. So this would be a fixed point. Okay, we're not looking for a fixed point. We're looking for a fixed point up to a complex number. So that's a complex number. In that case, this is called an eigenvector. And this guy is called an eigenvalue. Okay, there's not a lot of here. There's not a lot of, you can think of this as follows. V lambda I t. Okay, this is just, you look at the equalizer of this. In other words, when do you have t of v should be the same as a lambda of v? And so you have that. It really doesn't have a lot of categorical content. The main point is we're going to use eigenvalues and eigenvectors, and there's 3 main theorems about eigenvalues and eigenvectors that depend on what type of t we're dealing with. And so I'm just going to read them to you because it's something important that we're going to use. But the proofs are in the book. The proofs are 1-line proofs. The eigenvalues of Hermitian operators are real. So that's an interesting thing. These are complex vector spaces. This is a complex vector. This is a complex vector. But if T is a Hermitian matrix, then this lambda is real. Okay? That's going to have a major, I told you Hermitian matrices have to do with measurements in quantum computing, in quantum mechanics. So what that says is when you measure something in quantum mechanics, the outcome is going to be a real number. if you ask yourself what the temperature is, or how much time has passed, or you ask yourself the length of a table, it gets a real number, not a complex number. So that's a very interesting thing. Quantum mechanics is about uses complex numbers, but the real world seems to be all about real numbers. And so the relationship between the two has to do with this theorem. Let me just restate it. It's on page 278. The eigenvalues of Hermitian operators are real. Next, the eigenvectors of distinct eigenvalues for Hermitian operators are orthogonal. What that means is when you measure things and you get two different outcomes, if you measure this or you measure that and you get two different outcomes, then the real numbers are going to be different in some sense. Okay, and finally, well, what about unitary matrices? Unitary operators, let's say T is a unitary operators. The eigenvalues of a unitary operator have modulus 1. Okay, so they will be complex numbers, but they'll be complex numbers of a very simple type. Okay, great. So again, this was a mini course. All the mini courses are stop. Let's use what we did, and we used all the monoidal structures that we had, and we used the previous basic linear algebra, and we used it today. Okay, and we will use this stuff later on. But this is what's done in an entire class, and we did it in 2 hours. Obviously, we left out a lot of details, but it's a beautiful, again, linear algebra is a beautiful subject, shows up all over. This way of looking at it from this categorical point of view, that big diagram I just erased, is worth meditating on. It's worth really understanding. Anyways, let's foreshadow for a little. We are now finished chapter 5. We're going to go to chapter 6. What's chapter 6? Well, let's recap. Chapter 4 was about how categories relate to each other. Chapter 5 was about monoidal categories, this extra structure that we put on categories, including categories of vector spaces. Okay, great. Now, namely the tensor product and the direct product. Now, we're going to go on to chapter 6. We're going to talk about how functors, how two monoidal categories relate with each other. So we're going to talk about monoidal functors, and we're going to talk about monoidal transformations. Monoidal natural transformations. Okay, and then we're going to talk about coherence theory, which is a very important topic. It's going to be a lot of fun. Take care. Have a great day.